The essential question for today's lecture, which is number 2 out of 3, is what evidence supports the theory of plate tectonics? Again, what evidence supports the theory of plate tectonics? Let's start in the left-hand column of your notes. Please add the left-hand column, Wegener's evidence for continental drift. Left-hand column, Wegener's evidence for continental drift. Our only definition for this lecture, at least a new definition for this lecture, is going to be continental drift. So take down this definition. Continental drift is the movement of Earth's continents relative to each other. So the rock in the mantle is semi-solid, meaning it is solid, but it can move. It is plastic. These large continental plates seem to float on this semi-solid rock. They are moved by convection currents in the mantle, in that semi-solid mantle. Continents, because of this movement based on convection currents, they will move slowly over millions of years. And over time, form supercontinents, and then, again, over time, having those supercontinents break apart.
If you look closely at the globe, you will see that most of the continents seem to fit together like a giant jigsaw puzzle. The western coastline of Africa seems to fit into the east coast of South America, for example. The way they fit together is even more pronounced when one looks at the submerged continental shelves. In 1912, Alfred Wegener, a German meteorologist and geophysicist, suggested that the continents were once one giant continent which he called Pangaea until about 300 million years ago, when it began to break up and drift apart. But he had no explanation as to how this happened. It wasn't until the 1960s that scientists began to understand how the plates move.
Scientists are gaining more knowledge of plate tectonics every day. However, the theory of plate tectonics is a relatively new one, becoming widely accepted only in the 1970s. One of the first things that scientists noticed that supports the theory of plate tectonics is the apparent fit of the continental coastlines. This is particularly apparent in the way that the eastern South American coast and the western African coast seem to fit together like a jigsaw puzzle. This evidence led to the hypothesis of continental drift, which was developed in the early 1900s by a German scientist named Alfred Wegener. Wegener marshaled a variety of evidence in support of his idea that the continents may once have been joined. One of Wegener's pieces of evidence to support his hypothesis of continental drift is that similar landforms are distributed across oceans. For example, mountain ranges sometimes appear to be continuous on both sides of an ocean. The Appalachian Mountains in North America and the Caledonian Mountains in Greenland and Northern Europe formed when all three land masses were joined in the supercontinent Pangaea. As Pangaea broke apart, what had been a continuous mountain chain broke apart as well. Today, these mountains are separated by the Atlantic Ocean and several northern seas. Rock sequences have also been matched on opposite sides of the ocean. A second piece of evidence that Wegener cited as supporting his hypothesis of continental drift is when he noticed that deposits of glacial sediment had been found on opposite sides of an ocean. The position of these glacial deposits did not make any sense with the continents in their current position. Continental drift, or the idea that continents have moved in the past, seemed the only explanation for their distribution. The last piece of evidence for Wegener's continental drift that we will cover in this lecture is that similar fossils have been discovered in distant locations. The Mesosaurus, which is a fossil found in Brazil as well as Western Africa, are just one example of this phenomenon. Paleontologists continue to find more and more fossils that match on opposite sides separated by oceans.
As the 20th century dawned, geographers and geologists knew that mountains had risen up over time. That most mountain ranges were long linear strands. But they didn't understand why mountains had come to be in the first place. They knew volcanoes constantly changed the landscape. But they didn't understand what was producing them. They recognized that earthquakes were concentrated in specific areas, such as along the west coast of the United States and the island nation of Japan. But they didn't know why. And paleontologists were puzzled by the discovery of virtually identical trilobites in different continents. The one on the left found in central Iowa, and the one on the right in northern Africa. It made no sense. A big explanation was needed. That explanation came in 1912, when a 32-year-old German meteorologist with geographical inclinations, Alfred Wegener, suggested that around 200 million years ago, there was a supercontinent called Pangaea, and it began to split apart. His theory was called continental drift.
Well, let's start with the Eurocentric view of the Earth, the view that is so common in world maps. This is the map that led the early cartographers and geographers, for example, Ortelius, to think of continental drift because they could see a similarity of the shape here between South America and Africa, and they said perhaps they were together. In 1981, I was working in Liberia, which is located right about here. They were searching for minerals, and I started trying to understand where the minerals might be in Africa based on where those same minerals are in South America. And I didn't get a very good match. So it occurred to me to turn South America. I'm going to show you first where the traditional fits say it was. This is the original thinking was that it fit like this, but in the 1960s, we recognized that you had to take into account the continental shelf, so it moves off a little bit like this. But now look at, if you turn South America 90 degrees, look how well it fits. It's incredibly even at its edges.
That'll do it for our left-hand column dedicated to continental drift. Let's start a new left-hand column titled Evidence for Plate Tectonics. So a new left-hand column titled Evidence for Plate Tectonics. Initially, the hypothesis of continental drift was rejected. This was because Wegener could not determine the mechanism by which the continents drifted together and apart over geologic time. Wegener died in 1930, before scientists truly began to accept his ideas. Advances in technology allowed scientists to more thoroughly explore the ocean floors. Using new sophisticated instruments, they began to understand this mechanism that Wegener could not find. Scientists realized that Earth's surface is divided into tectonic plates containing both continental and oceanic tectonic plates. The hypothesis of continental drift then became incorporated into the theory of plate tectonics. Scientists use Wegener's evidence supporting continental drift to support the theory of plate tectonics. Scientists also discovered further evidence of plate tectonic movement. The theory of plate tectonics is supported by the relatively young age of the oldest oceanic crust. Earth's crust first solidified approximately 3.85 billion years ago. Earth's crust is constantly recycled through plate tectonics. If it were not recycled, all of Earth's crust would be expected to be the same age, about 3.85 billion years old. However, new oceanic crust is continually being formed at sea floor spreading centers. Older crust is continually being destroyed at subduction zones. Therefore, the oceanic crust that exists today is only about 200 million years old, which is much younger than the age of the continental crust, which can be even older than 3.85 billion years. Sea floor spreading centers provide other evidence for plate tectonics as well. Scientists can observe where the oceanic crust used to match up. This oceanic crust has now been pushed apart on either side of a mid-ocean ridge. Scientists have discovered the symmetrical age patterns of oceanic crust on either side of these mid-ocean ridges. They have also discovered symmetrical magnetic reversal patterns. And these matching patterns show very clear evidence that the oceanic crust is moving apart at the divergent boundaries of mid-ocean ridges. Magma wells up between the two moving plates, forming new crust. And scientists can directly observe new crust being formed at sea floor spreading centers. They then infer that older crusts must be destroyed elsewhere on the planet. Otherwise, Earth itself would be expanding. Observations of old crusts being destroyed at subduction zones confirm this hypothesis. And lastly, plate tectonics is also supported by precise measurements of relative plate motion. Scientists can use global positioning systems, GPSs, and other devices to track the movement of tectonic plates. Scientists now know that the average rate of plate movement for each tectonic plate. Some of the plates move faster than others, but the average rate of plate movement is just a few centimeters per year. At this point, you should be able to generate a response to the question, what evidence supports the theory of plate tectonics? So as this video comes to an end, please write your response to the question, what evidence supports the theory of plate tectonics, in the summary box at the bottom of your notes. Please do that now.